There we go. All right, say it louder. What are you going to drop the class for? We're layoff, people. Today we're talking about our friend. You're going to want to write this down. Differentiability. A tissue. Oh man. There we are. It's nice that you tell your mother you love her. Always, every day. Differentiability, folks, is what's the easiest way to word this? There you go. If you can find f prime of a, then f is differentiable. Okay? And I don't mean that you can find it like you know how to derive it. I mean like it actually is there if it exists. Let's say that. Exists. That's probably a better way to say it. Okay. It doesn't really matter. So you can find the derivative, it's there, it exists. Okay. A super easy way to think about it, although this is in like a very technical way, ready, is if you zoom in on a function at a point and it looks like a line, then f of x is differentiable there. Okay, it just has a slope, that's what it means. The function has a slope there. Okay, so let's look at a couple ways that this could, fall apart. Let's take a look at one of your favorite functions. F of x equals 1 over x. Okay, and let me add in the directions for this here. Determine where each f of x is not differentiable. Okay. So if I gave you a function and I said, hey, where is this not differentiable? I'm asking you, where can we not find the derivative? Okay. Can you what? Yeah. Okay. So first off, where's f of x not defined? At 0, because we can't divide by 0. If you plug 0 in, you don't get a point back. And if there's no point there, then you can't zoom in on it, so it can't look like a line, so it can't have a slope there. Does that make sense? So automatically, without even doing any calculus whatsoever, this function is not differentiable at 0. Easy enough? Okay, so over here, we're going to list ways a function can be not differentiable. Whoa, why is it moving this box? Get out of here. Okay, the first one, f of a is undefined. There's no point there, can't have a slope there. Sound good? We can see that graphically. I'm a big fan of graphing stuff. Graphically, 1 over x looks like this. Okay, there's no point there, that's easy to see. Also, if we were to find the derivative, we would get negative 1 over x squared. And the derivative is not defined at 0. Like you literally cannot find f prime of 0. It doesn't exist. Make sense? Okay, so we'll add that as our second way, even though they're kind of the same thing in this case. F prime of a is undefined also. Okay? Because they could be separate. There could be different things happening there. I'll show you an example in a second. Cool. This, much like continuity, it's a pretty simple concept, but we talk about it in a little bit of a complex way. So I think graphically is the easiest way to talk about these things. All right, so my second function, we'll call this number 1. We will call this number 1. If my pen wants to cooperate. is g of x equals 3x squared plus 4x minus 8. Everybody knows that's just a super sweet parabola. Okay? And g prime of x here is 6x plus 4. Cool. Turns out that derivative is just a line, and it exists everywhere. Make sense? So g of x, because it's not a weird function, it has no jumps, right? So anything crazy going on, is differentiable everywhere. Cool. So let's write this here. Another way to say that, if you want, is differentiable for all real numbers. Okay. Oh, and I didn't answer my question for number 1. I'm sorry, guys. I mean, we did. We just didn't write it. F of x is not differentiable at x equals 0. That's number 1, right? Everybody okay with that? So number 2, differentiable everywhere. Nothing fancy going on there. Okay. Number 3. Let's talk about this. This pen keeps going to sleep on me. Let's talk about the square root of x. Okay? And really, before we even derive it or anything like that, which we're going to do to check it out, let's think about what this graph looks like. Okay? The square root of x is just half of a sideways parabola. It looks like this. Okay? What is that not going to be differentiable? Just looking at the graph. What's up, Theo? Definitely not negative numbers, right? Because there's nothing there. There's no point there. And also, where's the graph stop? Where's it not continuous? 0. So it's not differentiable for any negative number or for 0. It's okay? The derivative, when you find it, should back that up. It should be undefined at those places. And it is. If we find the derivative here, which, come on, pen, h prime of x is 1 over 2 root x. Cool. So root x, which is in the denominator right now, we can't plug any negatives in there, right? So this thing's undefined for negatives. And now, you all know that I can plug 0 into a square root, right? Like if I put 0 into h, not h prime, h, I get back 0, right? The point 0, 0 is on this graph. But if I put 0 into the derivative, I get 1 over 0, which is undefined. Okay? So again, the graph stuff we're thinking about plus the derivative like function, they should back each other up. They shouldn't conflict ideas. So this thing is not differentiable for parentheses, really, negative. I'm going to write infinity. You can do the symbol. I spelled it wrong. Infinity to 0 with a bracket because we can't include 0. Easy enough. What? The bracket means all negative numbers and 0 too.
Oh, okay.
Okay, it means include it. Okay? If you wanted to write, so again, the question is where is it not differentiable? It's the same as that question is where is it differentiable? The answer is just the opposite, or the complement of the set. So if you want to write that, you would write differentiable for parentheses 0 to infinity. Okay? So the question would be, where is it not differentiable, or where is it differentiable? Same idea. Just you pick whichever set they're asking for. Okay? And real quick, let's talk about why the graph looks the way it does. Okay, just square roots, because we'll talk about other weird roots. Okay? The reason why square root of x gets bigger as we plug in bigger x values, everybody knows this, is because if you take the square root of a bigger number, you get a bigger number back out, right? So that's why this function increases. That's easy. Okay? But the reason why it bends the way it does, a function can increase like this, or it can increase like this. That's called concave up versus concave down. The reason why the square root function is concave down is because it treats bigger numbers differently than smaller numbers, right? It cuts them down more, basically. For instance, if you plug a 2 into here, it's not a 2. If you plug a 4 into here, the square root of 4 is 2, right? It's chopped it in half. But if you plug a 10 into here, 100 into here, imagine this is 100. Yeah. You all see where I'm going with this. it's going to turn that into a 10. It divides it by 10. So bigger numbers get chopped down more, which causes it to curve less and less, or increase less and less as you go up. That makes sense? X squared is the opposite. If you square 10, you multiply it by 10. If you square 3, you multiply it by 3. So bigger numbers get multiplied by bigger things, causing them to grow faster. That's why it bends upwards. Okay? Okay. The reason why I'm going over all that junk is because if we were to plug in, we'll call this one h of x2, to cube root of x. So sometimes students get a little confused when they see a root in general, and they're like, I can't plug a negative number into that. And that's not true. We can plug a negative number into a cubed root, right? Cubed root of -8 is -2. Okay? However, because it's a root, the graph of this thing on the positive side still looks the same. It just goes up a little bit less because I'm taking the cubed root now instead of the square root. Okay? Negative numbers get treated exactly the same, except they're negative outputs. So it's the same exact shape, just down here like that. Okay? Now, that doesn't help us with the derivative. It looks like that thing should be differentiable everywhere, right? But something weird happens at 0. This is going to be a new case for us. If we find this derivative, we get 1 over 3 x to the 2/3. And that's not defined at 0. Cool? You try to put a 0 in it, h prime, you get 1 over 0, undefined. The reason why that's happening is because if you were to zoom in on cubed root of x right at 0, it would look like this. Okay? It gets vertical at 0 for a second. And what's the slope of a vertical line?
0.
No. Undefined. The slope of a vertical line is undefined. Okay? That's because, a horizontal line is a slope of 0. As you increase the slope, it goes up more and more and more, right? Slope is a measure of how far up do you go for every 1 unit over. That's what slope is. Cool? So if I went up 100 and over 1, that's a slope of 100. Cool? If you went straight up, you're not going over at all. That's an undefined slope. Cool? And if the slope is undefined, then the derivative is undefined at 0. Great. Good talk. So that's actually another way that a function cannot be differentiable. So let's add that to our list. 3. There could be a vertical tangent. Okie dokie. Artichoke. So good. Another way, which I kind of skipped over with the square root function, it could also be, so let's make this number 4, I guess. F of x could be discontinuous. Right? We didn't talk about that. We didn't write that on our list. There's only one more, I think. So let's come back down here. The answer to number 4, by the way, is just not differentiable at x equals 0. Cool. So a super easy way to do this, again, you check the graph. Another easy way is to actually find the derivative and see what makes it undefined. Okay? But sometimes they're going to throw weird functions at you with like absolute values and stuff. It's going to be a pain in the butt. So graphically, it's a whole lot easier for that. Okay. Let's get weird. Let's talk about number 5. X to the 2/3. Okay. Now, this is another, so this is the same thing as the cubed root of x squared, right? So, the root and the power are like fighting each other, right? The power wants to multiply and make it bigger, while the root wants to take away and make it smaller. Who's going to win this fight? The cubed root or the square power? Which one's bigger? Cubed root. Yeah, cubed root's going to win, which causes the graph, it's still going to get bigger, but it does it bending downwards, concave down. Okay? Versus, we're not going to look at this one, but if we graphed cubed root x to the fourth, that's going to go up this way now. Okay? Versus this one is going to increase from 0 this way. What's in the middle of the cubed root of x squared and the cubed root of x to the fourth? Cubed root of x cubed, which is doesn't bend at all, just goes up. Make sense? Okay, so they're kind of fighting each other. The reason why I'm highlighting that is we know the graph has to look like that. I can also plug in negative numbers, right? I can plug in negative 8, I can plug in negative 100 if I wanted to. However, we're squaring them, which turns them positive. So we're going to see the same exact shape here, but it's not going to be down in the negative section. It's going to be up here like that, which looks kind of like a bird if you're drawing a picture in kindergarten or me currently. Okay? Okay. Guess where this is not differentiable? At 0, and you can see that when you derive it, right? Y prime is 2 over 3x to the 1/3. Not differentiable 0, definitely. So you can write that. Not differentiable at x equals 0. Cool. But that's not a vertical tangent. It's not a discontinuity. It's not undefined there. Okay? That point like that, when a graph has a slope coming in one way and then leaving out another way, that's called a corner. Okay? And if a function has a corner, then it's not differentiable at that corner. Yep, we're going to add that to our list of thingamadudes. Badoon. F of x could have a corner, and that's basically it. And some of those overlap, like being undefined or f prime being undefined. Actually, f prime being undefined is every single one of those. Okay? But when you define it by just deriving it and seeing where it's undefined, that's a pretty easy way to do it. Okay? So, in general, a function, you can consider a function differentiable if it looks like a roller coaster that you could ride and it would be a nice smooth roller coaster, okay? Like this right here, as long as it doesn't get vertical. Like, that's differentiable everywhere. Same thing with continuity. Like, it doesn't have to have a discontinuity. Just sometimes it does, okay? But if we had a roller coaster like this, that would not be a fun ride, all right? Okay? This thing's not differentiable here and here. Guess what kind of points those are called? Corners. That's it. Okay? What other kind of functions have corners? Absolute values have corners. So you'll see questions like that in this. Okay? So let's take a look at one of those. What are we on here? 5, 6. There should be another. Oh, I know why I skipped one. 6. Could be f of x equals the absolute value of something weird. You know, with continuity, we also had like piecewise functions. We're going to see piecewise functions in here too. Okay, that's what kind of questions pop up. So we'll go over a couple of those. I posted homework online already. I was going to wait till 8:30 or 9 o'clock to do it on Sunday night, but I did it early for you. Okay, good. Yeah, I know. So if you're asked where a function with absolute value is not differentiable, you don't really want to derive absolute value. Here's what I don't want to see, kids. I don't even want to write it. Do not write f prime is the absolute value of 2x. That is incorrect. You hear what I'm saying here? Do not do that. Okay? The way you talk about the slope of an absolute value function is just going to graph it. Graph the stupid thing. Do you know what x squared minus 9 looks like? Yes, 1 year. So, I don't know. What's it called where you say the same thing over and over again? Not really like a mannerism, but kind of like a neurotic thing. Flick makes fun of me all the time. Okay, I don't know. Some years I just say the same thing over and over again for some reason. Okay, I don't know if I have one this year. 1 year I say cool like 1,000 times a period. Yeah, it's not really a motto. It's more some like a nervous tick, perhaps. I don't know. But anyway, x squared minus 9 should come down like this, and it should keep going, right? It should come down and then go back up like that, and then do that. But the absolute value forces the negative part to bend upward, thus creating corners.
W.
Okay, W for Wayne. That's my middle name. Okay? It's a nice shirt. This will not be differentiable at those corners, but you got to know where those corners are. Where are those corners? 3 and negative 3. So, without doing any calculus whatsoever, we can say not differentiable at x equals 3 and x equals negative 3 because if we want to explain ourselves, there are corners. That's it. Okay? If you do have to talk about the derivative of an absolute value function, like if this question said instead of where's it not differentiable, find f prime of 1, okay? Then you still want to graph it, and you're just going to drive x squared minus 9, right? The derivative of x squared minus 9 is just 2x. But that means the derivative of x squared minus 9 in an absolute value is either positive 2x or negative 2x. Those are the only options. Do you see which piece of the graph we flipped over? That has a derivative of negative 2x. That's it. So the derivative of this piece right here is negative 2x, while the pieces that didn't move have a derivative of positive 2x. Because we didn't change those, right? That's just x squared minus 9. Now, this is not really the way to write this, okay? But that's graphically. Does everybody see the picture there? Like, yeah? If it flipped over, the derivative has changed sign. That's it. Because the function changed sign. If you had to write that out, that's a piecewise function, and it equals 3 different things. What am I doing? F prime of x is, it's either 2x, or it's negative 2x, or it's 2x again. It's 2x for the integral, or for the interval, when x is less than negative 3. It's negative 2x between negative 3 and 3. And it's positive 2x when x is greater than 3. Notice how I'm not putting any equal bars on there, because there is no derivative at 3 or negative 3. So don't plug them in. Easy enough? Excellent. Kaylee's having a good time. She's not going to drop calculus. She's going to finish it strong. Take Calc 2 next year. Have a good time. Okay, we'll take Calc 2 in college. Email me with all your hard questions. It's fine. Okay. A couple other weird things that we can talk about. Oh, I don't know what number we're on. 7, 8?
Something like that.
Okay. I'm just trying to throw you some weird stuff that could happen. That says, what? Let's get weird.
I want to make you a post emphasis.
Let's get weird. Okay.
Let's make him a post emphasis.
Yeah, I'll hang it up. That'll be good.
Let's put it up next to this graph. Is too.
Okay. Do you know what our sign looks like? It's the easiest way to think about these, especially if it's a weird function. It looks like sine, turned sideways, and chopped. Okay? It looks like this. And it stops, okay? Sometimes kids think that goes up forever. It doesn't. It stops at that point. It stops at the x value of 1, the y value, pi over 2. And it starts at the x value negative 1, y value, negative pi over 2. Because the graph does not exist outside of 1 and negative 1, that thing is not differentiable for anything less than negative 1 or anything greater than 1. Easy enough? Without doing any calculus. We also know it's not differentiable at 1 or negative 1 because the graph stops there. It also happens to be vertical. So there's a lot of reasons why that's happening. Okay? So we can write that without doing any calculus, but we can also do a little calculus just because I know that's what you want. That's what you came for. That's the derivative of that. If you don't know that now, shame on you. Okay? But we got a square root in there, right? And we can't plug any negative things into a square root. And what kind of number is going to make that square root negative? Anything bigger than 1 or anything less than negative 1. It goes together. It fits. The derivative tells me the same thing the graph does. Okay? So this one, not differentiable for negative infinity to, what do we say? Negative 1, including union with 1 to infinity. Boom. Okay, so I want this to be a relatively simple kind of topic. Yeah. Yeah, it just depends on the question. Like, where is this differentiable versus where is it not differentiable? Just answer whatever question they ask. What up?
Why does it have a bracket at negative 1 if you said that it doesn't really include it?
It's not differentiable at negative 1. So it does include negative 1 if you're telling me where is it not differentiable. If you tell me where is it differentiable, use parentheses. Okay? All right, and this is the last function we're going to look at like this. And then I'll show you some other weird stuff that could happen. Let's do p of x equals the square root of x squared plus 1. Now we got another square root, right? So sometimes kids just see square root and they're like, oh, x can't be less than 0. Cool. But that's just square root of x. If it's square root of something else, whatever's inside of it can't be less than 0. But guess what kind of number x squared plus 1 always is? It's always positive. So this thing's continuous everywhere, even though it has a square root. Does that make sense? Cool. So if you derive this thing, even though it's got that square root, the derivative is just 1 over 2 square roots of x. Come on, you. X squared plus 1 times 2x. Right? Right. And again, that's got a denominator, but it's never 0. It's got a square root, but it's never negative. Cool? Yes. We could definitely cancel out those 2's. Boom. Easy enough? And if we had to graph this thing, I like to talk about what graphs look like. Especially if there's only one x in there, even if it's got some weird stuff happening to it, you can figure out what's going on with this thing. Okay? Doesn't make sense that if you plug 0 into there, you're going to get a 1. Right. And the bigger x gets positively, like the end behavior, the bigger the square root of that thing is going to get. Cool? However, here's what's weird. As x gets bigger and bigger and bigger and bigger and bigger, that plus 1 matters less and less and less and less and less. Right? What's the square root of x squared? It's just x. It's a line. So as x gets bigger, this thing, it does curve a little initially, but it just goes up like a straight line. Okay? And if you plug in negative values, the same thing happens. It goes up like a straight line. Okay? And what's even cooler is our derivative verifies that. Take a look at this derivative. If I asked you, what happens to that as x goes to infinity, as I plug in huge, huge values? Remember how we look at this? What's the biggest thing on top? X. What's the biggest thing on bottom? Also an x, right? Squared x squared. Which means, as x gets bigger and bigger and bigger, the derivative just becomes 1, which tells you it's approaching like a y. Make sense? There's a lot of ways we can think about analyzing a function without doing a ton of work. Okay. Let me think. Let's do this. If I draw a big old graph on here, let's just go through and pick out the places it's not differentiable. Okay? I'm so good at this. There we go. So, that's my crazy graph. Do you see where it's not differentiable? How many? Let's count. How many places could it not be differentiable? I'm telling you, this is vertical over here, even though. It's going to be 4. It's going to be 4. Very good. Y'all can count. There's 1 here. What's that? Corner. There's 1 here because discontinuous. There's 1 here because asymptote is undefined. It's discontinuous. Lots of reasons. And there's 1 here. A vertical tangent. Yeah? Right here. It's hard to pick out sometimes, but yeah, I'm telling you, yeah. And in a problem, it's funny. Like if they give you a graph like this, they will specifically say f of x has vertical tangents at x equals 2 and 3. And it's not differentiable there. Okay? All right. So the most probable way you're going to see this, though, especially on a test in here and on the AP test, is with piecewise functions. All right? So let's take a look at a piecewise function. I don't know what number we're on, 9, 10. We'll say 9, 10. There you go. Okay. T of x for Tori, for terrible, for terrific. Okay. For Theo. You know what? For Toodle. I'll see you back there. Okay. You know let's say we had 2 functions, and one of them was 2x squared plus 3x, while the other of them was x plus 4. Oh, this is one function, sorry, defined in two pieces. There we go, that's what I meant. Okay, this could be on the AP test. Could be on my test. Just like we do with limits, right? Where does the limit exist? Where is it continuous? Now I can ask you where is it differentiable. So to be differentiable, the pieces, there's only two pieces here, right? They meet at 1. Or where the split is at 1. To be differentiable, we need them to meet, but we also need them to meet with the same slope. Otherwise, there's a corner there. Like if they meet and it looks like, let's draw it out here. So if this piece comes in like that and the other piece leaves like that, it's continuous, but it's not differentiable. Okay? Even if it's a positive slope, like let's say it comes in like that and then you have a slope like that. That's still not differentiable because it's like bending. It's breaking the curve. Okay? But if it leaves with exactly the same slope as it came in, now it's a differentiable. Again, it's like roller coaster pieces fitting together. They got to have the same slope or else the coaster's going to fall off. Okay? Okay. No, you don't want that to happen. So, if the question is, where is t of x differentiable? It's specifically going to be asking about 1. So that's where the split is. Okay? So, we plug 1 into both pieces, and we're going to find out that t of 1, the limit as t approaches 1 from the left and the right is 5. Can we handle that? So, remember, all we do is plug in 1, but if you had to explain why it's continuous, you'd have to go back to those 3 pieces. The limit is x approaches 1 from the left, t of x, equals limit x approaches 1 from the right, f of x, equals t of 1. There you go, t of x, whatever. Okay? All right, so that's not the question. We know they meet. That's good. Now we need to check the derivatives and see if they meet. Because if they're not the same at 1, then we're going to have a corner. So we check t prime. I know a lot of times kids see piecewise functions and they're like, oh, God, piecewise functions. But the functions inside of there will always be pretty simple. The same thing with absolute value. Okay, if you see those things, they're going to be easy functions to work with. So the derivative of this is 4x plus 3, and the derivative of that is 1. Okay, another weird thing. Even though there's an equal bar up here, it doesn't mean there's going to be an equal bar on the derivative, because the derivative might not exist at 1, so there won't be an equal bar there. Okay? Do these pieces meet with the same slopes? Now, one comes in with a slope of 7, so they meet at the point 1, 5. 1, 2, 3, 4, 5. But one comes in with a slope of 7, which is pretty steep, and the other one leaves with a slope of 1. There's a corner there. All right? And if you had to explain it, I don't think you ever will. Okay, but if you had to explain why it's not differentiable, you know how we have a left limit and a right limit? You can write out the left derivative and the right derivative. The left derivative at 1 is 7, while the right derivative at 1 is 1. There's a corner there. You can just write those words, the left derivative. Okay? No, we're not going to write now, because you're not going to see it, but sometimes AP exams surprise me with a question, but it's fine. Easy enough? And then the very last question you're going to see is something like this. F of x. You'll definitely see this on a quiz or a test or both. Ax squared plus bx minus 3 for x is less than 1. I know that's what you want to see. And 2bx squared minus ax plus 1 for x greater than or equal to 1. What is that? Okay? And the question's going to say these super sweet secret words in a very small font. Which one a big? Oh, because I zoomed out. Hang on, I'm having technical difficulties. Fine, can you guys see that? Thanks for I like that. Let's go. What kind of font do you think we need here? Like a 48. Ooh, that's not even that big. We're going all the way to the max. Find f of x. Nope, not find f of x. Find a and b so that f of x is differentiable. And if this, can I drag this out? Oh, good. There we go. We're almost done. We're on the verge of Friday. Or Saturday, Friday night. I know you got big plans, hot dates. Yeah. Have to work, even better, make some money. Okay. You know what we're going to do? We're going to plug 1 in for x. We're going to set those equal to each other. Right? There you go. Okay, you're right. We're going to substitute in 1. That's a good word. Good math word. They have to be equal to each other. So, we need a plus b minus 3 to equal 2b minus a plus 1. Okay? If that equation's true, it guarantees this function is continuous. Both the pieces go to the same spot. Right? Before I do anything else, I'm going to simplify this, get all my a's and b's together and stack them up, okay? I'll move all my a's over. So I'm going to get 2a. We're going to subtract 2b, so it's minus a b, equals 4. Everybody see where that's coming from? Okay? But I also need the derivatives to meet each other at 1. So all we got to do is derive this. It's just the power rule, and set those equal to each other at 1. So we're going to find f prime. I'm running out of room here. But f prime of x, I'm going to put it over here. Keep in mind, a and b are just constants. Okay? They don't have derivatives. Like, they just go away. We could derive them, right? Or if it's like a number with x, it just becomes that. So the derivative of ax squared is 2ax. The derivative of bx is b. The derivative of 2bx squared is 4bx. And the derivative of minus ax is minus a. And the constants go away. And the first one is still defined for x less than 1, and the second's for x greater than 1. Woo-hoo. Everybody with me? We're going to plug in 1. So with the continuity question and the limits test, a lot of y'all could get to the equations, and you messed up the algebra trying to find the answers. Okay, so I'm going to show you how you should do this to keep things simple. But if you put a 1 in there, you're going to get 2a plus b. Right over here. 2a plus b had better equal 4b minus a. Right? Right. I'm going to get all my junk together here. We're going to add a. So it's 3a. And we're going to subtract off 4b. Minus 3b has to be 0. There could be a number there, but there's not in this particular case. It's just a 0. That's fine. So 3a minus 3b equals 0. And I'm going to stack that right under here. I'm going to zoom in and write that again. I'm not like that. How thin that is. What were those equations? 2a. Anybody help me out? Minus b equals 4. Thank you. And 3a, 3b. Yeah. So you can do substitution and everything with this, but if I were you, I would just multiply to cancel out one of these variables. It's always so much easier. It's way less work. All right. So I'm going to multiply the top function, top equation, by negative 3. So, okay? I'm going to put it right underneath of this other one. If you do that, you're going to get negative 6a plus 3b, that's a b, equals negative 12. And I'm looking at these two equations right here. Everybody see where that came from? If you add them up, you will just get negative 3a equals negative 12, which means a had better be 4. Okay? Now, a lot of times we get weird fractions with this. This just happened to work out. I'm honestly surprised this was a whole number. Okay? So we could just plug a in and find b, but if you don't want to do that, or you have fractions you don't feel like dealing with, just do the cancellation again and get rid of a this time. Cool? So we know a is 4. I'm going to go back to these two equations, and to cancel out a, I'm going to multiply the top again by negative 3. So that's negative 6a plus 3b is negative 12, and I multiply the bottom by 2. That's going to make it 6a minus 6b equals 0. Am I messing this up? Is that right? Okay. So rather than plugging in and simplifying all these dumb fractions, let's get this to cancel out, and we end up with negative 3b equals negative 12. And for some weird reason, a and b are both 4. Okay, but you saw on the test, I made these up at random, guys. I'm plugging stuff in there. They're usually like 7 over 21 or 15 over 13 or something like that. Okay, so if you just do cancellation like that, it works out a little better. But that's basically it. Differentiability, not super crazy. You'll see definitely a question like this one on the test. Okay, probably one of these absolute value ones, like where is this not differentiable? Just graph it and tell me there are corners. That should be an easy one. All right, and then maybe a graph where I'll ask you where's it not differentiable and you just pick out the points. Okay? Oh, look, where's the top?